Okay, so I hope this is last time to fix things and start again physics beyond the standard model. And I was telling you that we were discussing if I should focus on one of those models and try to give you in wide details, or I just overview different directions of physics beyond the standard model, and it depends on your test. You may select, because all of them are still open. We have no guarantee that any of these models beyond our standard model will be the correct one. So the idea now, after a discussion with Shuaib and Marcelo, that we give you a flavor of each extension. And if this is good and bad, good that you have a kind of view of all physics beyond the standard model within a week, but very bad because things will be just touching the basis of each model and give the details or leave the details for you. And I am happy if anyone select any of those models and want to explore it more. I'm happy to work with him offline. Some of our colleagues already attend online, so normally we can continue on offline as well, or online, I don't know what's called. But during this course, I will try to start with a standard model. I asked it and they give me, seems wrong information, but they said that you studied already standard model. However, I prefer to review and to introduce at least the notation and the convention that we will use it later on. So I will spend the first lecture on the overview of the standard model, which already we lost half an hour of it, but we will take another half hour. And then I will discuss the evidence for going beyond the standard model and why we need physics beyond standard model. And then the third part is the directions of those models of new physics. And these directions will cover almost the parts that we will discuss, or the next lectures that we will discuss it in the next days. Okay. So, as I told you, first lecture will be about standard model and beyond. This is the simplest, hopefully, and the easiest. Is just the opening lecture. Then second lecture, I was quite optimistic that I may consider two simple extension, because I don't want to spend one lecture 2 hours in just one simple extension. But if you think that standard model still is not digested very well with you and the extension, we need to go step, it's up to you, we can divide it. We can take the extension of the standard model with extra one, and I will try to explain to you, or to claim, that the simplest and the most natural U1 extension of the standard model is the B minus L, U1 B minus L. Another simple extension is to go to 2 Higgs doublets instead of just 1 Higgs doublets in the standard model. So far, okay. Then, if we did this 2 simple extension in one lecture, then we will have the chance to go much more deeper and consider ground unified field theory, example of the simplest ground unified field theory, which is SU5. And the SU5 historically is the first ground unified, first gap model considered after the standard model, and then Baki, Salam, and other people worked in this model. So historically it's very important, very simple, very elegant. However, we will discuss it in details in that lecture. Then, is it challenging to give you an idea about supersymmetry, which is also necessarily an important ingredient for physics beyond the standard model. We try to convince you of this, and then how to improve, to add supersymmetry to the standard model and to construct what is known as minimal supersymmetric standard model, MSSM. Last but not least, the extra dimension. This is one of also possible directions of beyond the standard model. If we extend our dimension from 4 to 5 or more, this is extra dimension will play essential roles in explaining some of the problems that we may face it in the standard model. So, as I said, this is really too much, I know. We will give overview about each topic. If you think general overview or quick overview is not a good idea, we can just take one or two models and we do it explicitly. I am open for that and I have no problem. If you think, no, it's a good idea that we make a survey about all these possible models. And then, as I said, each one of you interested in one of those models, I can work with him the details of this. And each one work in some model in details, we will produce in notes, we distribute it with the others. So maybe we can, by the end, not of this week, but maybe the end of this summer, we will have 5 notes cover everything and everyone can read and even can discuss with the author, one of you, of these notes. And then we really enhance our knowledge quite quickly. So this is a plan. So let us start with the first lecture, which, as I said, standard model and beyond. And in this lecture, I will overview the standard model, or very quick review the standard model. And then, as I told you, we'll try to give you some evidence for physics beyond the standard model and try to convince you standard model is beautiful, is wonderful, it's very successful, but it cannot be the ultimate theory. We need to go beyond the standard model. And until now, all the signals, all the signature, all the results of the LHC run 1 and run 2, and we are now run 3, still giving some fluctuations, some anomalies beyond standard model, but no confirmation yet for, and people sometimes start to worry and say standard model, no physics. No, this is a life with particle physics. We do not discover every year or every even decades some particles, some proof of. If we will discuss this is in details during the course. That the discovery, if you see the Higgs, for example, is discovered after 60 years, more than 60 years from its proposal. So we have to be patient. And something like supersymmetry, for example, it's elegant. Can we find it or not? You have to give it a go until we confirm. And then we will discuss the direction, as I told you, for beyond the standard model. And you will find that the four topics I selected, or 5 topics I selected, are part of those directions. So, as I told you, this is the simplest and the easiest lecture of the 5 lectures, and this is the easiest slide in the first lecture, where we remind you that in the nature we have already 4 forces, you know very well. We have the strong interactions, electromagnetic interaction, weak interaction, and the gravitation. And you know the field strength or the interaction strength, if you normalize the strong interaction with 1, then this is the strongest, and the electromagnetic will be almost 10 to minus 2, and the weak interaction almost 10 to minus 8. Gravity is very, very, very weak, 10 to minus 45 respect to the strong interaction. And this is the reason why gravity is almost out of the scope of the standard model. And this is one of the issues that requires that if we want really to unify the forces, we need to incorporate the gravity in the game. And we will see that models like supergravity, which is a local version of supersymmetry, for first time bring gravity to the games with the other forces. So our standard model and our beyond the standard model that we will discuss in these 5 days will be mainly focused on the 3 interactions, weak, electromagnetic, and strong. Okay, gravity, keep it aside now for several reasons. This is too weak. It's classical only. There is no quantum version of gravity, and it's described by general theory of relativity, which is still on the other side of the standard model. Okay, the standard model, I will give you, quick review about how we constructed, and in fact, this is, as I told you, it's based on strong interaction, electromagnetic interaction, and weak interaction. And electromagnetic interaction, because it's long-range force, this is the oldest force we know with the gravity. So for our purpose now, electromagnetic interaction is really Maxwell's equation, and all this work done in the electrodynamics. And when we quantize it, it's wonderful theory. It is one of the best theory we know, and we formulated. And we now understand that it is based on what's called abelian gauge symmetry. I think you are familiar with this if you studied standard model before. So, to remind you, the idea when we studied Dirac equations, and we have this Lagrangian of the fermion or electron field. So this psi bar I gamma mu partial mu minus m times psi, this is what we call free Lagrangian of electron, or fermion in general, but let me say for electron because Dirac was doing for electron. This Lagrangian is invariant under what's called shift transformation, phase shift transformation. So psi bar goes to E to I alpha psi. Alpha is a constant. So this is what we call global symmetry, global U1 because it has just one parameter. So this Lagrangian is invariant under this transformation. Because if you substitute psi with psi prime, you get the same Lagrangian. L will be equal L prime. So the Lagrangian is invariant. Good. However, when we go to local symmetry, what is each time's admit?
Any person is trying to do enter.
Oh, okay. We have many people now. They are welcome. So when we make the symmetry local, not global, because global symmetry is not realistic, that you have a kind of phase shift constant symmetry will be invariant over everywhere in the universe. Local symmetry is playing much more serious, good. So if you take alpha of x function, alpha function of x, and psi prime will be e to I alpha of x psi, the Lagrangian is no longer invariant because the variation will act on alpha of x and generate partial mu alpha of x, which cannot be the same. And then the new Lagrangian will transform from L0 to L0 plus this extra term. Psi bar gamma mu psi times partial mu alpha. I think we all know this, even in electrodynamics we study, not even quantum field. However, I wanted to start from here to explain to you that electromagnetism, the procedure work with abelian U1, and then we go for weak interaction and strong interaction in a very similar way. How to make the Lagrangian, Dirac Lagrangian invariant under this local symmetry? You simply need to add vector field, A mu. And this vector field should be transforming in a way to absorb the variation partial mu alpha of x. So we changed the normal derivative to what's called covariant derivative, partial mu plus I e A mu. And then now A mu should transform. When psi goes to psi prime in this form, A mu should be transforming to A mu prime, which has 1 over E partial mu alpha of x. Now, if you replace partial mu with d mu, you are inserting some interaction between psi bar, psi, and A, and then you get this Lagrangian, which is now the original free Lagrangian L0 plus what we call the Li, the interacting Lagrangian, which has E psi bar gamma mu psi times the vector field mu. Psi bar gamma mu psi, we know this is, we call it the current J mu times the mu. So this is the interaction. So the conclusion that for local symmetry, there is no free Lagrangian, no free electron. To have a local symmetry, you have to have it interacting with a vector field, which we call it now as a photon. Because we need also to think about the kinetic term of the electron comes from this term, psi bar gamma mu, and the mass term. What about the mu? We add just the mu, and it appears on the interaction terms. So is it just auxiliary field, or it could be dynamical field? Dynamical field means it should have a kinetic term. So in fact, yes, it could be dynamic, and we look for how to write the kinetic term of the mu. So we find that we construct what's called the field stress tensor F mu. You know, I'm not giving you from scratch. You know this, so I'm overviewing. And even the next part, it will be kind of overviewing, assuming that you will go and fill the gap. Anyway, so the field strength sensor will define, like for a billion, for just one vector field mu, partial mu minus partial mu, and from this term you construct the kinetic kinetic term, or the free Lagrangian of electromagnetic fields, which is LA, it's 1/4 F mu F mu. F mu is invariant Lagrangian under Lorentz, because this is a dummy, under the gauge transformation as well, because F mu itself is invariant, because if A mu bring partial mu, it will be partial mu alpha, and this will be partial mu alpha cancel, so F mu will remain invariant, and of course F square will remain invariant, and then you can have the final gauge invariant QED Lagrangian in this elegant and nice form. The kinetic, so it's a free Lagrangian of the electron, the interaction term between electron and photon, and then the interaction free Lagrangian of the electromagnetic field of the photon. All together makes the QED. And this is, you know, this nice, and this is a Lagrangian, which when you take it and use Euler-Lagrange equation respect to the degrees of freedom that you have mu as a degree of freedom, you have psi as a degree. Then you get either, if you make Euler-Lagrange equation respect to psi, you get Dirac equation, but not free Dirac equation, but with a source from the electromagnetic field. If you do it for the mu, you get Maxwell's equation, and the source will be the electron, will be your source. So this is a wonderful QED Lagrangian, which we work it since many years, and we're very successful. We quantize it, normalize it, everything's fine. Few remarks here that from the construction, we don't have mass term. We have mass term for psi, for electron. Because the invariance psi bar psi, the mass term is psi bar m psi bar psi. So the phase shift, global or local, doesn't really prevent this term. M psi bar psi will remain invariant. So M in principle can be included. You will see in standard model with a weak interaction, this term will not be included. Okay, but now for just simple U1 and just simple electron, for example, this will be allowed. No term for mu, because the mu transform, as we said, to mu plus partial mu. So mass term like this will generate partial mu alpha, which is not absorbed, and then this term will violate the symmetry. The mu is invariant under Lorentz, because these are dummy, but is not invariant under gauge transformation. So the U1 gauge transformation prevent the mass for the photon, and this was good because we need the photon to be massless. And this is we will discover to be bad when we go to the weak interaction, because we want the mediator to be massive, because this is not long-range forces like the electromagnetism. We need massless photon, massless mediator. This is short-range force. So the mediator should be massive. And how to generate mass, this is the issue we will discuss there. So this is so far so good. Another important remark that we could use, we have a battery alpha that it changes A to mu to mu prime, and they keep everything without any change. So I could choose alpha. For example, if I have a mu, a partial mu, a mu is not zero, for example, I can choose alpha such that partial mu, a mu prime that I choose it to be identically zero. Okay? Take any a mu, act with partial mu, and then choose alpha to make it vanish. Since it is free, like a free function, a arbitrary function, I can choose it to make this condition. And this is called the Lorentz condition, and this is shown that there is some redundancy in the degrees of freedom in mu. They are not all of them are fundamental. There is some, degrees of freedom that we can fix. And this is one condition. There's several conditions, but this is one condition, an important condition, because it is keeping the Lorentz invariance. So we choose partial mu and mu, and we call it Lorentz condition, Lorentz gauge, to have a condition about on mu, and of course from this you start with 4 mu, A0, A1, A2, A3. You have this equation, it's just one equation, so you reduce the degrees of freedom from 4 to 3. You discover that it's still possible, even with this condition, you can play again with alpha, like what I gave here, for example, to choose partial alpha by partial t to be minus A0, and you cancel A0 prime in the new frame. So you can even reduce it from 3 to 2. And this is what we know experimentally, that the photon has a 2 polarizations only, 2 degrees of freedom. However, we all usually work with 4 degrees of freedom to keep Lorentz invariance and to keep the theory invariant under Lorentz, because this is help a lot in handling the theory without any mistakes. However, we need to take those constraints into account in the Lagrangian as a Lagrange multipliers or whatever in the detailed analysis of this QED. So this is the QED that we know, one of the best, and I wanted to remind you that was quantum electrodynamics with this simple Lagrangian obtained from simple procedure like this. We were successful to calculate, for example, quantity like what's called G-2, for example, which is kind of a prediction of the Dirac equations and confirmed with a quantum electrodynamics. We measured with loop levels up to the 10th decimal, 10th what's called number after the decimal. Can you imagine? We calculate and we are consistent with the experimental result up to 10 to minus 10 or 10 to minus 11. So far. So this is, for that reason, I'm saying this is one of the best theory really we have so far. Based on the gauge symmetry. I am trying to start to convince you how solid our really physics, the idea of the gauge symmetry. So of course, symmetry by itself in general in physics is very crucial and played very important roles. But I am focusing on gauge symmetry because on all directions beyond the standard model, I prefer to go with a gauge symmetry. Maybe some extension, some changing here or there, but I keep gauge symmetry as a guide for my going. Otherwise, you leave the standard model, you go in the dark in any directions, you add infinite particles, fermion, gauge boson, without any guidance. This is not really an interesting scenario for me. The scenario of the gauge symmetry and extending gauge symmetry, that what we are talking about, this is really done in the 40s and 50s. Okay, now when people realize that there is some other interaction different from the electromagnetism, in beta decay, for example, Fermi was the first one to formulate the beta decay analysis and interactions, and it was based on the decay of neutron to proton, electron, and neutrino. Then people believe in gauge symmetry like me, for example, they try to construct, and this is the way, I don't know who did this, first one did this, Fermi or somebody else, but this is helped us to reach the standard. I will tell you the story. So people think about, this is like, we have NP transition, so we have a kind of vertex. Instead of electron positrons or psi bar E gamma mu psi, we could have kind of a psi bar B gamma mu psi N. N goes to B. Okay? So we could have this bilinear. There was an electromagnetic, there was mu, the gauge field mu. We don't have gauge mu because we E plus E minus produce photon, here we don't produce photon, we produce electron neutrino. So in our beta decay analysis, if we wanted to do the same things for this beta decay similar to the U1 electromagnetism, I have to think about mu, not in this mu, but think about mu. Instead of mu, we have this psi mu, gamma mu, psi electron. And then I have a kind of Lagrangian, in some sense, effective Lagrangian. I have it like this term psi mu gamma mu psi E bar and times psi A gamma mu psi bar with some coupling constant, they call it G-Fermi. Okay? So this is very simple. I wanted to make it, very simple to compare it with what we know in the electromagnetism. So I replace mu with the outgoing particles there. Outgoing particles, 2 fermions. So we reach a kind of 4 fermion interaction. Proton, neutron, electron, neutrino in this format. Then we discover that this is called beta decay. We have also positive beta decay, where the proton can go to the neutron, electron, positron, neutrino. And this is essentially a Hermitian conjugate of this type. So in principle, you extend the effective Hamiltonian with this element. Then people start, yes.
So here in this Fermi Lagrangian, so here to visualize this things like a neutron and a proton and a neutrino and electron interact at this vertex.
4-point interaction, yes.
Yeah,
yes.
Exactly. That's why we.
And then we will come. Things doesn't come suddenly. Goes step by step. Any theory goes step by step. So we start with this Fermi where we don't have any just phenomenological explanation for decay happened to this simple formalism to make it similar to the electron. Then we extend it to this. You will see how it goes until we even assume there is mediator W boson, and then how to relate this to gauge coupling Fermi, G Fermi, and then how things takes us to the weak interaction SU2 left across U1 and so on. So nobody said, and then I said, let me make the weak interaction like SU2 left times U1. From where? For that reason, when you explain it to the people who's not working in the field, why SU2, why U1, why? Why? Because the history, 20, 30, 40 years to build this, to reach this. In fact, standard model, Salam, Winding, Glashow, even before SU2 left across U1, was trying to build with just the SU2, and it didn't work. We need semi-direct product with U1. Anyway, we are now up to this point where we have effective Lagrangian 4-point interaction, 2 terms. And then people realize that these 2 terms, vector, 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 vector. What's this vector, vector? This 4-point interaction comes from gamma mu contractions. This is what we call the vector, vector. And this is also the same. But mathematically, it could be all type of contractions. You could have a scalar without gamma mu. Is it possible? Yes, in principle, yes. You have kind of row times vector, you get singlets multiplied by another singlets. You could have an invariant term saying scalar, scalar. Or pseudo-scalar, pseudo-scalar. What is pseudo-scalar, pseudo-scalar when you have gamma 5? People in quantum field theory usually do this list of all this invariant quine. So in Brazil you could have vector, vector. So this is just one option. Why it is here only VV, why or V? Why there is no scalar? Why there is no tensor? Why there is no axial tensor, axial vector, and also pseudo-scalar? People start to think maybe we have all those contribute to the interactions. And in fact, in this case, the Lagrangian will be generalized to this format, where we have operator OI, which contains either 1 for the scalar, gamma 5 for the pseudo-scalar, vector gamma alpha, tensor sigma alpha beta, and gamma alpha gamma 5 for axial vector, gamma 5 for the pseudo. Then people realizing that, but beta decay, in fact, you don't need to consider all this. It is only can be described or can be used only S and T or V and A. For some reason, they choose V and A. For that reason, we have what before standard model was called the V minus A interaction of vector. Okay. So far, so good. Then we discover in 56, remember 33 was Fermi with beta decay. For that reason, I'm saying physics needs time. You need really to take your time to build your theory. It's not just a matter of couple of years and you come with everything. So 20 years, almost 23 years now, we discover something experimental, that parity is violated in the weak interactions. And therefore, the beta decay should be modified really. You cannot so do you hear us now? Hello?
Yes, we can see.
Okay, sorry for the interruption, it was a net. Okay, so I was talking about the beta decay and how we are using all the information sometimes at this moment to improve our Lagrangian, our effective Hamiltonian, our theory in this. So when we discover non-conservation parity, we have to include it in our effective Hamiltonian, and then we add term, and it becomes like some coefficients plus coefficient gamma 5. And then 56, 1 year later, Landau, very important people, Lee, Yang, Salam, proposed that the neutrino is massless. At that time, they cannot see any mass for the neutrino, so they assume it is massless. And to explain how it is massless, they assumed it is two components, spinors, with definite chirality that we call it left. Because with definite chirality, you cannot build the mass for this particle, and because the neutrino appears to be massless, so they make this assumption. This was a good assumption at that time because the neutrino appears as massless. But once we have this assumption, again we go and modify our Lagrangian, our Hamiltonian. Instead of the neutrino, we have to use neutrino left. Remember, now the proton and the neutron still remains both chirality, left and right. And then we discover also quark by that time. So the effective Lagrangian will be changed to not B and Yeah, we will rewrite it in terms of even the quark components. As you can see now, instead of p neutron couplings or intervertex or currents, you will have like u bar d, u bar gamma alpha d, c bar gamma alpha s. So each time that our information is increased, our modification and our correction to the Hamiltonian is done. So now we discover that there is a mu partner of the electron, similar particle, mu particle at that time, very close, very similar, of the same family of the what we call it leptons now, different only in the mass, semi-charged, same everything. And in fact, they realized that the decay can also go to muon and neutrino, and neutrino now becomes electron neutrino and muon neutrino. So you have to take this information and you increase and you modify your Hamiltonian and your current. So you have now electron gamma alpha electron neutrino bar and the muon gamma alpha muon neutrino bar with the original NP. And when we know that quark sectors, the interaction currents or the charged currents becomes like electron neutrino, muon neutrino, tau, can also tau neutrino. All this is a lepton. All this is we combine now with L or L gamma neutrino L. And all the quark sectors, 2 bar gamma alpha T, C bar gamma alpha S, T bar gamma. We cannot start from the beginning in 33 with T bar gamma alpha B. There was no top quark or bottom quark, even mu or tau. So each time we have some development in our technology, our discovery, we have also development to our theory and our Lagrange. We end up with this.
Should enter the
This is I didn't. Okay, I should explain this one. So we agreed here that I wrote it here, but I didn't. We agreed in the previous slides that the neutrino only is left-handed, and the proton and neutron or quarks and the other electron, for example, they are massive, so they have left and right. Then came Feynman, Gell-Mann, Marshall, and the others said it's not natural. You know, one is left-handed, and then interact with electron, for example, has a 2 chiralities, but which type of chirality will interact with the neutrino? Will interact with the left or with both? Okay, their proposal that the interaction will be with the only left. So left-left interaction. Okay. Because we know that neutrino are massive now, but at that time we don't know. So it was very good wrong assumption, because this has helped us to construct the standard model in the format that we know now. If we kept it like this and we kept, I'm not sure if I'm mute again or not. No. Is it shared, the screen now?
Yes, Professor.
Yes.
Shared. Okay. Okay. So, Muhammad, right? Muhammad was asking, because I didn't comment about the first line, that after Salam and et al. Assumed the neutrino is left-handed only, they came and also assumed the other particles are massive and the other particles have left and right, but they assume that naturally, according to their imagination, that left-handed will interact with the left-handed components of those particles, although they have right-handed, but they restricted the interactions of the weak between the two left, because you know you can try to justify it as you want, but was just their assumption, and it turned out that this assumption was correct and was nice and was developing our model in this form. So now the interaction becomes left-left, and this is the reason why we have U left, T left. Where is the U right and T right? There, but not interacting in the weak interactions. In the beta decay, which will be the interaction governing the beta decay, is a weak interaction. U right and the D right and the E right, all those will participate in the electromagnetic interaction, will participate in the strong interactions. Okay? Just because a neutrino is not included in the electromagnetic and strong, they only interact weakly and only left-handed. So they proposed that we should have really left-handed. And there, I think, in their mind, something like this intermediate gauge boson, because neutrino left-handed, you will have a vertex W, and this is left and right. So which one you couple with W? In fact, now when we have neutrino right, E right, you will have what's called W right, and this is in the left-right model. So their assumption, although was not really exactly correct, but very, very interesting at that time, very simplified the model at that time. And then we will have W, which is interact only left-left. Because if W, you know, four-point interactions, maybe it was not so clear. I have neutrino left and electron with both chirality. We have just vertex coupled with another vertex. Who cares? No, but when you think about W, intermediate gauge boson, you have this is left and this is something left and right. You have to tell me W coupled with left, right, left, left, with which coupling? They decided to have neutrino left, E left, W, with a coupling of G, what we call it G now for the okay. Yeah, and now G Fermi will be defined like coupling from here over the mass of MW, because W is rather heavy respect to the 1 GeV low energy that we are considering in beta decay. So this is defined G Fermi. G Fermi will be just G squared over MW squared. And in fact, this is all this known before the standard model construction, and G Fermi is known experimentally from the decay and all this work done in 1933. So we know the value, and we expected this coupling from different process. So we were able to estimate the mass of MW with ATGV, known before the standard model. For that reason, is not one of the prediction of the standard model, the mass of the W. Mass of the W is used in the standard model to fix the vacuum expectation value. And then the real prediction was the mass of the Z boson. In fact, the prediction of Z boson and its mass. Well, this is the real prediction, but W was assumed before the construction, and the mass was known from the comparison with the G Fermi.
So even before considering the X.
Before going, yeah. However, I'm going in the construction logically and historically. So sometimes the logic sometimes disturbs the historical, but this is, I guess, more or less. Now we come to our main objective, to write the weak interaction in terms of the gauge theory, because so far I make just a vector gauge, vector boson, intermediate gauge boson, and is not yet the gauge in the form of the gauge theory. So now comes to the pioneer work by Young and Niels, when they generalize the abelian U1 to non-abelian. SU2 as an example, or SUN, or whatever, non-abelian. Let us start with SU2 because this is the relevant one for our weak interaction. Why SU2? Because in fact, why not U1 for the weak interactions? We can speak about higher, but minimally U1. Are you forced to go to SU2 or U2 or SU2 is a isomorphic? Yes, we are forced. Why? Because you have the gauge boson that we mentioned here is a charged, not like the photon, just massless and just one photon. Here is a charge. At least we have two, W plus, W minus. So at least we need two generators. And in fact, when we construct the standard model in gauge field terminology, we were trying and we aimed to have two gauge. Okay, we are there. No,
no, it's a problem here.
Okay.
Think it. Yeah, switched off.
I think it's coming.
When we move the switch off. Okay.
Okay, good enough. So I hope the colleagues online is listening and seeing the slides. So now we are talking about the one comment. Yes, okay, thank you. So about the non-abelian, in particular for SU2, and we will start with the free Lagrangian as usual, as we did with electromagnetic interaction. So now the psi is doublets. So as I told you, doublets now, everything should be really constructed in the 2x2 matrices. For M, for example, is M times the identity matrix. Gamma mu is already 2x2 matrices because it's acting on psi, which is a doublet. Okay, that's fine. And now I make the phase shift transformation, which is now psi bar, or psi prime is e to I 1/2 tau dot lambda. Why tau? Tau because we need to have the generator of the 2x2 matrices, which is about the matrices, so that this is will bring you, because it's act on the doublets psi, so it cannot be anymore just alpha, but lambda dot tau. And then we have really tau alpha, lambda alpha, or tau I, lambda I. So we have three constants, not just one alpha. Lambda now is a 3. Why? Because I started with doublets. Doublets bring to me the generator of the 2x2 matrices, what we call it SU2. And this is 3 generators, and then each one multiplied by some constant lambda. So this is the reason why we have 3 lambda, not just one, even constant lambda. Okay, this Lagrangian is invariant as long as lambda is a constant. Now, once we promote lambda to be function of the x, again, we will have the same problem that alpha, the variation of the psi will bring some variation with this lambda and partial alpha lambda multiplied by tau. So you need to really have a singlets from the matrices that you play with. And to absorb this extra term, you need to introduce now 3 fields, not just 1 field. Vector field in general with the index mu or alpha, this is a space-time. And now I is 1, 2, 3 to absorb each derivative of each lambda. So we have partial alpha lambda I, and then therefore we added introduced the vector 3 vector A alpha I. Again, in the same way, we have to change the normal derivative to covariant derivative, and this covariant derivative now contains this vector field tau I times AI. The indices alpha is a space-time matched with the partial alpha, but I with the tau I for the sum over the generators. This is the way to change the Lagrangians such that it will become invariant under local symmetry. And in fact, you do it as we did before. This is the covariant derivative u psi bar psi and the m, and then you also add the extra term or the kinetic interaction terms for the field mu. And now this f alpha beta, since for 3 fields, will not be just like partial alpha A beta minus partial beta alpha, but we'll have also cross term by epsilon ij AI aj with alpha beta indices. In fact, in the abelian, this term is 0 because the cross term of one vector with itself is 0. For that reason, I don't remember if I make a comment or not. Photon has no self-interaction. There is no interaction photon-photon, for example. Here we could have interaction with non-abelian H boson because we have this extra term from F to mu, and when you square it, you could even have power 4 terms. Now the interactions Lagrangian will be quite similar, but with tau psi alpha, and this is we call it current times the vector. And the current now you can adjust it. It's 1, 2, 3, 1 and 2 because it's multiplied by tau 1 or sigma 1 and sigma 2, and sigma 1 and sigma 2 it has 1 plus sigma 2 it has I, and you can adjust it to have 1 plus I2, 1 minus I2 instead of working with current 1 and the current 2. You could make a linear combinations of 1 and 2, and you can have it like Hermitian conjugate. Okay, so this will be with kind of positive plus, and this is negative, and this is coupled with negative 1 minus I2, and this is exactly we are constructing to give you something charged W minus with a current G plus and G minus with a current W plus to have a charging invariance. And there is a neutral component which is A3 alpha with a current G3. As I told you, J1 plus I or minus I is constructed from tau 1 plus I tau 2 or tau 1 minus 2, and this tau plus will be 0, 1, 0. Therefore, this is where you take the doublets components from the link between ups and downs. So if you have the doublet like UD, the interaction will be U bar gamma mu D. And therefore, this different particles will have different charges, and the net charge of this current will be +1 or -1, depends on the position of this. So instead of neutral currents that we have in electromagnetic interaction, or even A3, you have a particle, anti-particle, the same particle, electron positive, but now it mixes the doublets, mixes the first components and second components of the doublets. So this is what we have, epsilon minus, epsilon 1, this is not a charge, this is a component. I told you about it in the first slide here. For the first component, epsilon 1, and 1 is minus 1. This is the isospin, because one, you take it 1 or minus 1, or half or minus half. So this is really mixed between two different components in one multiplet. So in fact, you have relations between the multiplets will have a kind of hypercharge, and due the charge will be T3 plus half y. T3 is different for different components. Hypercharge is fixed for all doublets. So delta Q will be exactly delta 3, and therefore the current here will be charged similar to the isospin difference here with plus 1 or minus 1. And therefore, if this is plus 1 current charge, this is W should be W minus, or charged with minus sign. This is current with minus sign. This is will be gauge boson with a charged plus sign. And this is creates a two gauge boson that we were looking for, W plus W minus, to mediate the weak interaction that we were expecting. The surprise that we have one extra term which is neutral. And as I told you, people was trying to be economical and said, okay, this term could be the electromagnetic interaction. So our SU2 will have W plus, W minus, and the photon, and we unify everything in one group. It would be nice. But this A3 constructed from SU2 left. So it's interact only with left hand. Electromagnetic interaction interact with right as well, as we said. So it cannot be weak interaction. Also, A3 mainly interact with neutrino, because a weak interaction came with a neutrino interaction. Neutrino is massless, neutrino is chargeless under electromagnetic interaction. So A3, which couple or interact with a neutrino, because if you take J3 alpha, you will find that it has a neutrino as well in the bilinears. So it cannot be electromagnetic interaction. What that then? This is new neutral current. This is new neutral current, and this is one of the main prediction of the standard model, as I told you. And we discovered that the gauge boson of this neutral current is in fact the Z boson. Now, similar to the abelian, non-abelian interactions were massless gauge boson. All the gauge boson are massless. Therefore, we need to generate mass. And now we need to invent what's called symmetry breaking or spontaneous symmetry breaking to generate mass. Okay, one question: why you need mass? Just put mass term in the Lagrange. You break the symmetry. Okay, I break it. I break it explicitly by adding mass term. In fact, this is not good, because you break it explicitly and then you destroy the weakened gauge interaction, and you destroy all features. And the most important features we need the gauge symmetry to remain with us was related to the renormalizability quantum. Maybe we didn't discuss quantum field there, but really you will lose the renormalizability when you add mass term by hand. So this is the reason why people want to keep the mass, so the gauge invariance on the Lagrangian level, and generate mass from the spontaneous symmetry breaking, means from the vacuum. The vacuum will violate the symmetry, not the whole Lagrangian is violating the symmetry. And when this setup is done, and we will see, there was a PhD thesis by Toft and Veltman to prove that the outcoming theory from this spontaneous symmetry breaking is really renormalizable. It's not just looks like renormalizable as we can see. No, it is calculable, and they do the calculation and they show that it is renormalizable. And for that reason, we respect this mechanism very well to generate the mass term for W boson. This mechanism, as you will see, also produce kind of new scalar particles, which we call the Higgs field. And we appreciate this mechanism more and more when we discover the Higgs boson. People before discovering the Higgs boson was even in doubt that standard model with Higgs mechanism, maybe just mathematical trick, maybe if it is not discovered, we have to rebuild the standard model. So for that reason, as I said in the introduction, we have to be patient with our faith because it's not so straightforward, it's not so simple. But usually, really, it gives, impression that the human mind is really great, is predicting a lot of things, which was really expecting is not that true. Anyway, spontaneous symmetry breaking, and we start with very simple example, and in fact, this is known even in condensed matter physics. And when you have a scalar field with a potential like this, the minimum of this potential, if the coefficient of the mass square term of mu square is positive, there is a minimum with around 0, identical, and the symmetry is exact. However, if you change and you vary and you get mu square negative, the 0 value of phi becomes unstable minima or ground unstable maximum, and you will have kind of several minima. In fact, circle. Here is 2 points only in this example. So you have the two choice. If you have general, you could have a circle with a face which takes all these values like minima, and now the selection of one of those two minima. This is what we call it. We will break the symmetry, and we have to calculate we have to build our theory around two minimums. We have to select one of those two minima and make our perturbation and our fluctuation around this minima. So we are shifting everything to one of those minima. Symmetry is broken, but interesting results are obtained. So this is an example of what will happen if I shift my field, which is complex field, the real part around the V plus sigma, and the initial part as itself has a 0 value. So now you go to the Lagrangian with phi, divided in terms of sigma and eta, you will get this extra term, and you will find that the sigma field is dynamical and it has a mass term. So we started with phi field with this mu square, which was negative. And now you have eta kinetic term, but there's no mass term for eta. So we end with two neutral particles, spin 0, yes. Sigma has a mass, but eta is massless. It's called the Gauss symposium. And there is a theory here. If you have a symmetry and you break it spontaneously, you generate one mass term, but you generate also Gauss symposium. Gauss boson is massless, and massless is an issue because this is long-range force, a scalar force. It will affect everything in our universe. You have to discover, blah, blah, blah. So the thing was, simple exercise was called the same theory. Total number of degrees of freedom, we start with complex phi, we end with two real phi, sigma and eta, fine, but we have a problem with a massless particle. Then it comes the Higgs mechanism. The Higgs mechanism said, okay, you are talking about global symmetry. You have just this phi field with just a global, with no local gauge field around. So you just break the symmetry of the phi with the VEV of the phi, and you generate mass for phi and the eta massless and so on. But let us do this if you combine the scalar field with a vector field. Okay, so instead of the partial covariant derivative partial mu phi, you will have a covariant derivative, not normal derivative, covariant derivative, where you have the field in mu exists. So you have interaction a mu phi star, a mu phi, you have a mu phi star, partial mu phi, you have all these type of interactions when you change normal derivative to covariant derivative. Okay, then what will make the difference in the symmetry breaking? Nothing. You have the potential as it is, you minimize it, and you shift it as usual. You have invariance, you have the gauge symmetry now. So the symmetry will be broken is a gauge symmetry, not the global symmetry. Because the global symmetry there was just lambda, now lambda of x, and you have A transformed in this way as usual gauge section. Okay, now if I take the mass term square negative of the same potential that we used, you get, as we said before, phi of x, which is v plus chi exponential. We do it in polar coordinates instead of sigma plus eta, Cartesian. You have 2 degrees of freedom, chi and theta. In previous slides, I was calling sigma and eta. So, but the same. You can write any Cartesian in polar, in phase shift and the sum square. And take this and substitute. Now the vector field will be affected because it coupled with phi, and the phi is shifted as a v plus chi, and the phase. The phase will disappear because exponential in this, and this is a nice way of writing in this form. And in fact, now it becomes like scalar field partial mu chi, where one of the degrees of freedom remains, and it has a mass term, which is a chi square term from here, so it gives you t square times chi square. This is a mass term, and the mu, which was coupled with phi, now coupled with chi. It's not, but it has some value, the constant times the coupling g square will play the role of the mass term of A. So you generate mass term for the gauge boson via the value of the scalar field, and the Goldstone boson, which was corresponding to theta, disappeared from the Lagrangian. So in the previous slides, I was mentioning that the number of degrees of freedom is the same. I start with 2 degrees of freedom, I end with 2 degrees of freedom. One of them massless, but it's still there. Now it is disappeared. So I started with mu and phi, which has 2 components. I end with mu and the chi only. So there's a missing in the degrees of freedom. No, mu, when it was massless that I started with, it has a 2 degrees of freedom that, as we mentioned before. But now, when it becomes massive, it becomes a 3 degrees of freedom. So this is absorbed the degrees of freedom, the missing degrees of freedom. And this is what we call that the degrees of freedom, or the imaginary part of phi, is eaten by the vector field and it becomes massive. So this is the story of symmetry breaking and generating mass term for the gauge field. And in fact, degrees of freedom now is consistent: 2 from pi, 2 from A before symmetry breaking, 1 chi, and 3 A's after symmetry breaking. Okay, so the degrees of freedom is okay, and this is the way, the mechanism we learned to use to break the symmetry and generate mass. All this is a standard model in very quick, which I should assume that you already know, and I start from beyond, but I didn't. Standard model. This is, as I said, all this is a real preparation for this. Standard model now, not only SU2 left, but also U1 hypercharge, but also SU3 strong interaction. Because, okay, the time was not allowing me to go to the details story of SU2 left across U1. As I told you, SU2 left only cannot contain the electromagnetic interaction. A3 is another neutron. So we are forced to include U1. Okay, we can include U1 electromagnetism. Then you have SU2 left with interaction. But in fact, not really, because in the construction, we have the electromagnetism will come from the linear combination of the neutral gauge boson and the U1 hypercharge, because hypercharge also there is some details. I don't know if you studied or you know or not, but all this, I have a new book in quantum and standard model, and all these things in first 6 chapters is given in details. So I think you can download it from library genes or whatever. It is England press, so I don't care about it. Anyway, so this is a standard model, SU3. Also, we built it only with a weak interaction. Now, what about SU3? We do it in the very similar way for the strong interacting particle, which is quarks. Okay, and the quarks has both all type of interaction, SU3, SU2, and U1, but leptons only this one. In fact, we added like direct product. You know, there is no really merging. You see here SU2 left and U1 are really connected. In fact, we try even to have electromagnetism from this. Doesn't work, so we have electromagnetism from these two groups together. And we will talk about symmetry breaking of SU2 left across U1 goes to U1 electromagnetism, which is exact at low scale. So there is really type of unification, type of connection between the SU2 left U1. Strong interaction is really orthogonal. We bring it just to, you know, you could study strong interaction SU3 for quarks independent of all this. But we know quarks also interact with weak. So let us make SU3 plus SU3. No real unification, okay, in this. So for that reason, we said the standard model is partially unified our interactions. And for that reason, we will think about SU5 as a real unification of all this gauge group in one gauge group, SU5. When we come to SU5, if we will have chance to come. So this is now SU3 cross SU2 cross U1, and as I told you, everything will go similarly as we defined in the previous slides, in the preparation to come to this slide. And the Lagrangian of the standard model will now be understood. So do you have after, you know, F mu, the field stress tensor for SU3, the clones? We have 8 clones because SU3 is a matrices 3 by 3, and it will have 8 generated. Now, for weak interaction SU2, you will have this F mu A, and A is 1, 2, 3. And now for U1 hypercharge, you will have another field stress tensor that we call it for an electromagnetism F mu, F mu. And then we construct, you know, all the doublets and the triplet. Depends on doublet under SU2, triplet under SU3. Charge it with some number under hypercharge. So really, you need to now to understand. So sometimes we show explicitly it is a doublet because we show the standard, the weak interacting part. But you have to realize that this is doublet and the singlet under SU3 because this is lepton, has no inter. But this one is a triplet, means each component U and D is 3, and 3 you can make a triplet, fundamental triplet. You write UR, UD, I don't know, red color, red, green, and whatever colors that we call it. So we explicitly show this, but implicitly we know that the triplet of the quarks are there. This is the singlets under SU2 left, but now it is triplet under the right, and charged as well, and so on. So we construct now with a covariant derivative. Importantly to note that du for the lepton L will be covariant derivative, which is defined like normal derivative. So for the quark will be normal derivative times you add the gauge field of the SU3, G mu A, 1, 2, 3, up to 8. And now for SU2, you will have W. And for the Y1 hypercharge will have. But for the lepton, no strong interaction, so you will have partial mu minus G2 T A W A 1 Y hypercharge and so on. Neutrino, for example, neutrino is a charged, is a singlet under. Neutrinos are like the lepton. It's part of the FR. I wanted to say about the right-handed U right or E right. F right in general, it depends. If E right, this will be like this because it has only hypercharge, no strong interaction. Yeah, because it is a singlet. But if it is Q right, it will have this part of it. Okay. But I call it F right. This is times. It should.
Fermions doesn't feel the strong interaction.
No, fermions in general, quark or leptons.
Yeah.
If it is quark, I have to write this as L right. And the Q right, I have to write partial mu minus IGS TAG plus this. Okay. So this is a nice standard model Lagrangian, and then we break the symmetry in the same way, but now we have, instead of just the scalar field phi, we will have doublets phi, because you are breaking SU2, not just simple ones. So you have again doublets with hypercharge 1, you construct your Lagrangian, and the d mu, this means we are making now Higgs mechanism because the gauge field are there, so we will not have a Goldstone boson, but we will have mass for the gauge boson. And similar way, you will have the potential in this way for the doublet power 5 dagger phi is singlet with mass term, and this is a quartic term. Again, we assume the coefficient of the mass term mu square. I am surprised that everybody accept that I assume the mass term square of the potential to be negative, because this is mass term. You take it in square and the negative, strange. Yes, it is strange, and this is why people, was not so happy with the Higgs mechanism until we discovered the Higgs, because you are assuming your coefficient of the mass term negative square. However, yes, we understand that this is not the physical mass. This is just the mass term in the Lagrangian that you start with. We call it bare mass, and the physical mass you obtain after you break the symmetry, and there is no phi, but one of the component will be. Still, but you start with something in the Lagrangian which need justification. In the standard model and all this work done before and with the standard model, there is no justification, because if you take it mu square positive, you will get 0 VF. You have to take it negative square and to generate non-vanishing vacuum expectation value. In models beyond the standard model, in particular supersymmetry, will show that the mu square, in fact, you started with some high scale positive, and due to the running from gut scale or high scale to low energy scale, it derive some contribution to make it negative, and then the symmetry is broken at this scale. And this is explained why the symmetry was exact at high scale. W boson was massless, quark massless, everything massless at high scale, and they started to generate acquired masses at lower scale when the universe is cold, or the energy will go down until we reach the level of breaking this symmetry. Anyway, we'll come to this point later when we motivate physics beyond the standard model. If you go and minimize the potential as normal, and you accept this minus mu square term, you will get the vacuum of the scalar field different from 0. This value v, which is given from mu square over lambda. Remember, minus mu square is minus is taken outside, so mu square here is positive. Otherwise, you will not be able to define the square root to get real value. And once you get the value, you break the symmetry. We are making very careful choice for the vacuum to be given for neutral components, not charged components, so that you break the symmetry and you keep the electromagnetic. You don't break electromagnetism, because we don't want to generate mass for the photon, and we want to keep the electromagnetism invariant. From this setup, you get the mass for W and Z, and as I told you, from W and Z, we know the mass of the W. You can really get the vacuum expectation value. You find it is 174, or depends on the square root in your definition. You take this value, you predict the mass of the Z, and this was one of the important, really, success and prediction for the standard model. Now, for fermion masses also, we started with massless fermion, because we from this Lagrangian, we have masses comes from left and right, but we have left-handed doublets and singlet right-handed. So to construct it, you have to couple with a doublet scalar Higgs. So doublet is a giving you singlets, coupled with a singlet, this will give you singlet term, which is infinite. So it was, there is no mass term to start with, but there was L bar phi or Q bar phi U. When this get vacuum expectation value, it gives you V, and now this will give you components from this E left bar, E right, which is the mass term of the electron. And then the electron or the quarks or other particles will generate acquire mass of order V times the coefficient, which is the Yukawa term over some. So the mass of the quarks and leptons are generated after the symmetry breaking. And all of them are proportional to the vacuum expectation value of the Higgs. So this is the reason why we said the Higgs is the source of generating the masses of the gauge bosons and the fermions as well. Nice, but not all of them is 174. Yes, because we have Yukawa couplings. So this Yukawa couplings what makes different values for the masses. For example, the top quark, if you allow Yukawa coupling to be of order 1, you get the top quark of order the vacuum expectation value. And this is the maximum value we can get, because otherwise you will have larger Yukawa coupling larger than 1, and this will be non-perturbative. So to keep the standard model perturbative, you need to have Yukawa less than 1. Fortunately, the top quark, which is the heaviest top quark mass, is order the vacuum 174. Okay, what about the bottom? What about the others? Well, you need to go now and to assume smaller Yukawa coupling. But we have the up quark 10 to minus 3, and you have charm, I don't know, 1 point something, and the top. So there is different order of magnitude discrepancy. Yes, that's true, and this is opens a question about the Yukawa, the flavor symmetry and the flavor theory. We have it here. How to explain the hierarchy in the fermion masses? We understand now the fermion masses are related to the vacuum things, similar to the gauge bosons. Gauge bosons was nicely given in the vacuum times the gauge coupling. Gauge coupling is determined from the interaction. So now Yukawa is arbitrary, really. And even Yukawa is, you cannot, not like the gauge coupling, you cannot determine from, okay, how many Yukawa coupling are 19. Let me make some 19 experiments over 19, some process, and try to fix one by one. It's not possible because the Yukawa are not physical at the end of the day. You diagonalize it, you get the masses, and you get the VCKM, the mixing matrix. And the mixing matrix, we fix it in this way. Made experiments and we fixed term by term, which was not good. We want to predict it, but at least we fix it and we know. So the Yukawa is parameter that is not really, is in the hidden sector. It gives you the physical mass, physical mixing, but it doesn't appear directly in the interaction. So for that reason, it became still puzzling. What about neutrino? Neutrino is massless because neutrino has no right-handed, so the neutrino has no term to construct it in this level. Neutrino appears in the left-handed leptons, okay? But when we have this file to get the 0 P, you couple E left with E right. You can get phi delta to convert the vacuum, and you get the mass for the upper component. There is no term in the upper component neutrino right. So this is the reason why we said if it is massless, then the neutrino right should not be there. And when we started to know that it is massive, we started to insert again neutrino right to the models, but this is not standard model, this is beyond. Anyway, some terminology about standard model Higgs, maybe you already heard. Standard model by itself predict there's a scalar field called the Higgs, but it doesn't predict the mass because it's a mass, as I mentioned in the previous slide. MH is just a square root 2 lambda times V. What is lambda? Lambda is a self-coupling, self-interacting coupling. In the Lagrangian, lambda here, lambda 5,4. Okay, so when we generate and get the masses of the chi field after the symmetry breaking, one of those will get P squared and lambda chi squared. So lambda is playing role here in defining the mass. Lambda is coupling, not Yukawa coupling, but the self-interacting coupling, which again could be up to 1 for perturbative, could be small, could be large, we don't know. So the standard model predicted the mass square root lambda times a vacuum. If you take square root 2 lambda, if you take lambda of order 1, you can get the mass up to 700. So this was like upper bound. If we do not get Higgs mass up to 700, then the standard model will be in trouble, because either you assume lambda larger than 1 and you will have non-perturbative regime in the model, and this is an issue, or the mechanism is not really trustable, not reliable, and there is something wrong. Fortunately, we discovered less than 700 by March, 125. But there was no prediction to be 125. And when we go to supersymmetry, I will show you that there was a prediction that it should be less than 130. 130. So can you imagine 130 and we get it 125? So I was always saying, this is really even indirect hint, say something, because if we discover it 135, we will rule out the model. So since it is not ruled and it was 125, we should give some credit. Anyway, now in the standard model, this was a limit, and fortunately we respected this limit and we get it 125 GV in 2012. So this is the interactions of the Higgs with the gauge boson, because the Higgs is essentially weak. It's coming from the doublets. It's left-handed doublet, so it interacts with hypercharge, and so it interacts with SU2 gauge boson W and Z. It is neutral, so it doesn't interact with electromagnetism. It has an interaction with self-interaction. It has an interaction with the fermions. So fermion, this is a Yukawa, but I told you, Yukawa disappeared. Give me the mass. So the coupling will be not Yukawa, because if the Yukawa still survive in the vertices, I would make a lot of experiments to fix it. But it gives me the mass. Mass over vacuum. Okay, I calculate and I get the mass. Also, the mass is not predicted. It's calculated, but not predicted. Someone is coming now. So this is the interaction with the fermion, interaction with the self-interaction HH, again with mass of the H square over V. Again, lambda disappeared. This is the reason why we cannot. But maybe lambda, this is H disappeared here. Maybe cubic term given in terms of lambda and V. So hopefully there is some analysis to really make some measurements for lambda. Yes?
So this upper limit
Yes.
Is upper limit predicted from the standard?
Perturbativity of the standard model by assuming the lambda less than 1. We will come when we come to supersymmetry. We
should be lower.
Much lower, 130. And the reason for the time being that the lambda is no longer free parameter. It's coming related to the gauge coupling. Once you have it related to the gauge coupling, then you have fixed prediction. Okay, so this is now before discovering the Higgs, people was trying all possible masses from 100 to 1 TeV. Really, and you see the lowest or the smallest new branching ratio for the Higgs decay is gamma gamma. because there is no direct. If I told you H is a neutron, has no interaction with a photon. So how it decay to gamma gamma? This is via the one loop. It goes to top bar, and then triangle diagrams TT bar and TT bar. So it goes to gamma gamma. So this is one loop. So it is possible, but since it is a loop, it is suppressed. And this was quite smooth. However, this small signal, in fact, was one of the processes that we discovered the Higgs, because gamma gamma, it turns out that LHC can be bought much easier than BB bar, which is the highest, because this is quartz, and quark mixed jets, and the background of a lot of gluons and jets and blah, blah, blah. So this was a clean, and then the second ZZ bar, ZZ, this one, it is here, but it gives you ZZ and K2 L plus L minus, 2 L plus L minus, is still a good option to discover. ZZ has a large value, as you can see, but when it goes to L plus L minus, it's dropped, the branching ratio dropped a little bit. So, however, the ZZ and the gamma gamma was two good channels to discover the standard model Higgs. So this is detailed, as I told you, anyone want from any lecture to go in details in one subject, just let me know and I proceed with you. This is the discovery at LHC in 2012 in Atlas and CMS. This is the gamma gamma. You see, just a small peak around the decay weight. This was giving the signal around 125 GeV, and this is really was a great moment for particle physics. This is a ZZ to 4 leptons, and this is, you can see that here is a discovery, this is a Z boson, here is a Higgs. The red color of this is really the signal of the Higgs decaying to ZZ to 4 leptons. Okay, everything so far, you know, a lot of channels, and usually is not exactly what you can predict it from the standard model, and the gamma gamma in the beginning was a little bit far. People imagine that maybe new physics and supersymmetry will play a role to explain it, but now the measurements again closer to the standard model. So it's a small fluctuation, but I think overall everything was fine with the standard model prediction so far. Okay, in these 2 hours, I tried to summarize the standard model, which course by itself, you know, I'm sorry that I give it, but better to start, better to you know, give you very quick overview about standard model then just start with a beyond standard model, and then I talk about problems in the standard model which we will see together. Now let me summarize the standard model in one slide. So the standard model, according to our definition, it's 4-dimensional quantum field theory, because each item I will mention here will be, you know, very important when we go beyond 4 dimensions. This is a standard model. If you go beyond 4 dimensions, this is something else. So it is 4 dimension and quantum field theory invariant under Lorentz and one-Q. This is external symmetries, okay? Space-time symmetry. Now, under local symmetry, or what we call gauge symmetry, we have, and we agreed, we didn't show in details, that we have SU3 for strong interaction, SU2 left, and U1 hypercharge for the weak and electron. And the breaking down from these 2 symmetries for electron test, this is the name exact, like gluons are masses. So this is the local symmetry. If you play with another local symmetry, another gauge symmetry, SU2 left equals SU2 right, because neutrino right, and such. This will take you to something else, and you understand it. It is point particles, all quantum field, right? But we also assume that our particles, quark and leptons, fermion, every range W, are point particles. Do we need to specify this? This is obvious. No, it's not obvious, because we could extend it if we assume one-dimensional object, string, for example. So string is a generalization to this point, and we go beyond the standard model from that point. We have a 3 fermions, quarks and leptons generation, 3 generation. People try to build with 4 generation, more generation, less generation, extra fermions. All this beyond the standard model. Standard model with the 3 generation only. Why 3 generation? Well, we built standard model with a 3 generation because we feel that the universe or the nature has only 3 generation, or at least our interactions give us a feeling that we have only 3 generations. In fact, we are going with our feeling when we have only 1 generation, and then 1 extra particle that's strange, and then we add this charm, and then we add the bottom, then the top, and energy cannot accommodate more than that. So we are happy with the 3 generations. Could we have more generation? Maybe, but this will be beyond standard. And all type of beyond the standard model, I will mention to you that it goes beyond one of those types. No right-handed neutrino. The mistake I told you by people constructed standard model at that time, that they assume neutrino as massless, because the technology at that time doesn't show any mass for the neutrinos, and therefore they assume it not just left and right is not contributing or whatever. No, just left-handed. Okay, and they ruled out, completely removed the right hand. So the standard model, by definition, no right hand. So now people say, okay, standard model with extra singlets, which we call it right hand, fine, constructed, but this is first step beyond standard model. You can make it like, you know, just as the right-handed neutrino, something odd, which is just coupled with left-handed to give mass, doesn't interact with any other particle, doesn't play any role in any phenomena, in anything. So you take it very high, gut scales or intermediate scales. Are you happy with this? I don't know, but yes, and you can, if you just construct the standard model and you add extra right-handed neutrino just to get the mass of the neutrino, and you make it completely decoupled, maybe, but I don't believe that it will work this way. Symmetry breaking with 1 Higgs doublet. We did everything with 1 Higgs doublet. Why 1 Higgs doublet? Minimality. Remember, if I didn't stress, but if you catch it, we have a problem with constructing the co-interaction. You remember the leptons, I showed you L with phi and E right. And when we went to quark, we said quark Q bar, phi tilde and E right. Phi tilde, I told you, you multiply by tau 2 to convert the verb from downstairs to upstairs to generate the mass for the quark. Nice trick, but in other models, we use at least 1 scalar for down sector and 1 scalar for up sectors. 2 Higgs doublet meaning. Why 2? Maybe more, but why standard model only with 1? Just for minimality, but there is no any reason behind it. Okay, but anyway, now standard model, the identity of standard model is 1 Higgs doublet. If you take it simple and you said I add 1 Higgs doublet more, sorry, it opens a lot of things, and this is beyond the standard model. This is not standard. We call it even 2 Higgs doublet. We don't call it standard model with 2 Higgs doublet because there is a lot of details. Another issue in the standard model, as I told you, no gravity included, and there is no candidate for document at all. Even left-handed neutrino, when we were massless, people thought that it may help to a stable massless law. But unfortunately, since it is massless, it is relativistic and it cannot account for large scale structure. We need really I will try all the time from now on to mention about dark matter and related things to dark matter, because the GSU conference will be mainly about that things. So better to prepare ourselves also to understand what they will talk about. So this is really the definition for the identity. I usually say items to define the standard model. So if you are having any questions here, you are happy with this, please keep it in your mind that this is how we define the standard. 4 dimension with this local symmetry, with 0-point particles and 3 fermion, no right-handed neutrino, 1 Higgs tuplets. No dark matter and no gravity. If I have 10 minutes more, then I will flash a few evidence for physics beyond standard model. I already mentioned the first one, which is a neutrino mass. Neutrino is discovered to be massive, and no doubt now that neutrino has a small mass but not zero mass. And this is due to the oscillation that people discovered in the neutrinos. So now we need to modify, and we now to include right-handed neutrino. And we, as I told you, is not that simple. When you modify, you will find, you open the box, you will find a lot of things. You add right-handed neutrino. How to explain? We heavy neutrino, light neutrino, you invented something called the seesaw mechanism. We will come to this, but I want to hear from this slide to convince you that we have at least one experimental evidence to go beyond the standard model and to generate neutrino mass. Dark matter. Dark matter is since 33 like beta decay, but the progress in the beta decay was much faster. It remains until almost 40 years until people started to consider seriously to explain when they measured rotational curves. And the rotational curves, in fact, over 1,000 galaxies, spiral galaxies, confirm this shape of the observed curve. So expected, according to Newton's law, that the rotational curve, the velocity anyhow, now if matter, visible matter is focused in the center of galaxies or something like that, it will go like V proportional to 1 square R, and it will drop like this. Go far away from the center of galaxies, you will have the velocity goes down. However, we have almost flat. So there is no explanation for this fact, and people came with the assumption that this is may need to assume that okay, the visible matter are allocated or concentrated in this central galaxy, but maybe around this, the dark part of this, it contains a matter but not visible. The dark matter. And when you have it like this, you make the mass now as a function of R, because when you go out, you still keep, you have to work with matter density. And then you could cancel the R dependence and D would be remain constant. Is it assumption? Yes, but we need to work hard to prove it. First of all, to find out the property of this dark matter, source of, how to generate it. Standard model as a particle has no particle like this. It should be neutral, should be stable. So we don't have any neutral and stable except the neutrino left-handed, but it is relativistic and it cannot really help us here. After discovery of the Higgs, and we got the mass 125 GeV, you remember lambda was the coefficient times the vacuum give the mass. So now you can calculate, you get lambda. Lambda will be essentially 0.012 or something, 11 or something like that. Okay, but this is at low scale, at the time at 100 GeV, at the mass of the Higgs. As you know, in quantum field, the couplings are energy dependent, and you study the explore of the running of the coupling up to God scales, and you find that lambda goes from 0.1 and it could cross the 0 and becomes negative at some 10 to 10 GB or 12 GB. Depends on the small variation in alpha S and meso, because the running is loop effect. So what's the problem if it comes negative? It's serious problem, because now the potential that you used in the standard model to make a vacuum expectation value is not stable, and is don't say this is the bias scale. I don't care. In fact, our universe starts in the opposite way. It starts from very high scales and then drop until you. So if it was unstable and with negative coupling running away and so on, then it never comes to the situation where we have minimization for the potential that breaks the symmetry. So this is an issue, and there is some solution that you go to 2-hex doublet or some other beyond standard model that shift this a little bit above the 0 value. So this is theoretical, but is an issue. Another theoretical issue is called the Higgs mass hierarchy. The Higgs mass, we discover square root 2 lambda VF. Okay, this is, we fix it 125. But now if you calculate the one loop correction, because this is quantum field and scalar field, you will find similar to the electron. The electron has this loop correction, which is called the logarithmic. And this is mass correction. It's proportional to some scale, lambda, but in terms of the log and some coupling alpha over pi times n. So you get even lambda of order gut scales or blank scale, you get factor 10 for 19, 10 to 19 times the log, you get 19, but alpha electromagnetism 10 to minus 2, or if you use very small correction, about 20% of the tree-level mass that you start with. So that for that reason, the electron mass radiative correction was not a problem. For the Higgs, the radiative correction was a serious problem, because this is the loop that generates radiative correction for the Higgs mass. And if you calculate it, you get logarithmic similar to the electron, but you get something called quadratic. The lambda scale of the divergence, lambda square. And this is making it crazy, because it's lambda 10 to 19 GB. You take the tree-level Higgs, which 125 to 225 plus blank Higgs. Make it very long. So you need really to stop this, to protect your Higgs mass. And this is one of the reason why we like supersymmetry, because it solves this problem in a very elegant way. So this is another problem, maybe theoretical, but an issue in the standard model. So we have two experimental neutrino mass dark matter, two theoretical so far, the running of the coupling and the Higgs mass hierarchy. Another, I would say this is experimental, the baryon asymmetry, matter-antimatter in the universe, the ratio that we have it for baryon minus and baryon antibaryon over the, almost no antibaryon, almost baryon. The ratio is 10 to minus 11. Why matter and antimatter in the beginning of the universe after the Big Bang was produced equally? Why we end up with only matter and there is no antimatter? Why there is baryon, no antibaryon? Well, there is several scenarios to explain this via CB variation and baryon symmetry, baryon number variation, and so on. But all this cannot be accommodated in the standard model. Standard model has CB variation, but not enough. Okay, so we need really to go beyond the standard model to explain this matter and baryon. And I have to tell you, even beyond the standard model, the explanation is not it's not well, it's not finalized yet. Another more theoretical or philosophical, if you want, questions like why SU3 plus SU2 Can we have a much more simpler gauge group like SU5 or SU10? This is what we'll discuss. How this is partial unification. Can we have real unification, can we have a force unified better than the partial unification? Also, the electrosymmetry breaking, this minus mu square term that we consider to break the symmetry. Why three families for quark and leptons? And masses and the discrepancy of masses of the quarks and leptons. And also now the neutrinos, the mixing in the quark sector is something like hierarchical, and the VCKM like diagonal, almost diagonal with a small off diagonal. Now the neutrinos, the mass matrix, the mixing matrix is almost all elements of the same order. Where is the gravity? Can we have quantum theory of gravity? What's called cosmological constant. This becomes serious when we have late expansion in our universe and dark energy. We don't have any candidates in the standard model for dark energy. So a lot of still open questions, and I think serious questions as well, that standard model is not at all aware of. It's not dark energy doesn't the cosmological constant. This is a constant of Einstein and gravity, not in the standard model. But dark energy, we don't have dark matter to talk about dark energy. So I think we have some rooms to copy on. And this is last slides to start next lecture tomorrow about beyond the standard model, the direction for beyond the standard model. I think all these problems that we mentioned and all the entities or the identity we define the standard model will take us to one of those directions. So you can extend the standard model by extending the gauge group. Okay, and as I told you, tomorrow I will start with very simple extension, just add extra U1, and we'll show you extra U1 how it change things dramatically, I would say. Or extend the hexes from one hex doublet to two hex doublets. Okay, you will find not only one hex, you will find the charged hex, you will find pseudoscalar hex, you will find heavy hex, and so on. You could extend the matter content, right-handed neutrino at least. Matter means for fermions, so you need to extend the right-handed neutrino. By the way, sometimes when you extend this, you are forced to include this and this automatically. But sometimes people try to do independent or by this for simplification. To understand the masses hierarchies, you need to talk about flavor symmetry. So in addition to local symmetry, gauge symmetry, you may start to introduce also, you say the standard model is based on space-time symmetry, Poincare, gauge symmetry, SU3 plus SU1, and flavor symmetry. Flavor symmetry could be global, local, discrete, whatever, but this flavor symmetry will give you the mechanism to explain the masses of the fermions and the neutrinos. You could extend the space-time when you go to extra dimension. You could extend the local symmetry, space-time symmetry. You go to space supersymmetry. Supersymmetry is not ad hoc assumption. It is really taking 4-dimension space-time to another extension with some fermionic degrees of freedom, and this is called supersymmetry. We will discuss this when supersymmetry local version will bring gravity. This is supergravity. You could extend the point particles nature or feature of the part and standard model particles to a one-dimensional object, and then you will end with a superstring. Each of this type of extensions give you different theory with different predictions. So, depends on your test. As I told you, I'm happy to start with any one of those, or I give you 2-3 of this type of extensions. And anyone interested with any one of those 3 or example we will consider, or other example, I am happy to work and explore it with him, online, offline, here, and even from Egypt. You are welcome. So enough. I told you I will take half an hour that we lost it in the beginning. So now I am in my time. I don't know if our colleagues there are still with us. Do you have any? Do you hear anything? Do you hear anything already? Hopefully you were able to follow. I saw that the number still remains 6, so this is good number as I understood. Because you expected 2, 3. Okay, so do you have any questions for today's lecture? The people here were asking from time to time. You didn't ask anything.
Yes, Professor, I have a couple of questions.
Please go ahead.
Yeah, the first one is about the Higgs mechanism.
Just the participant. No, this is well. Okay, I'm with you.
Yeah, okay. The first one is about the Higgs mechanism. We have that the Higgs mass depends on two values, V and lambda, but also they can be related to each other by this value of mu squared. So can you repeat, please, at the end, how those values are obtained for experimental purposes, or how these experimental people obtain this kind of values?
Okay, I'm just trying to see you in this screen, but it doesn't matter, I can hear you. So let me go now to the slides you mentioned. I think you mentioned this slides where we have the vacuum is given by mu square over lambda. I make height and I can.
Yeah.
No, this is what show me or show him. Okay, show all of us. Okay. Oh, no, it doesn't matter. Okay. Okay, so I think you are talking about this slide, right?
Yeah, yeah, Professor.
Okay, so as I told you, the potential V of phi, you can see now in the middle of the slide. V of phi, we just have, as before, very simple potential, but phi now is doublet. So it is phi dagger phi singlets multiplied by some mass term mu square that we should take it to be negative square. Then lambda phi dagger phi to power 4. Now we have we started with two parameters, mu square, which is essentially negative, and lambda, which should be positive, because to avoid, to make the potential unbounded from B. Okay? You minimize, you get vacuum expectation value of order mu square over lambda. Now, the vacuum expectation value is real value, and now this is fixed in terms not of mu square and lambda, but in terms of the mass of W, because the V is giving the mass of W, so MW is G times V, square root 2 GV. So in fact, we are determined V not from the theoretical parameters, but from the experimental value of MW. Okay, so now you have V 174. You can in principle say, okay, I know the value of mu square and I know the value of lambda, or I have a relation between them. That's fine. The important that mu square will disappear and it doesn't show in anywhere. Lambda will show only in one or two places. Lambda will show in the mass of the Higgs in this term, MH square root 2 lambda V. So V is fixed. We from MW, as we said. Lambda remains arbitrary. So now lambda, after we observe the mass of the Higgs, we were able to find the value of lambda. And lambda, we find it of order 0.11, 0.12. So now the second parameter is fixed. You can say, okay, I also get now mu square, because 145 equals square root mu square over lambda. I know lambda, I can, but no points to do that because mu is not playing any role anymore. Okay, for that reason we said mu is like a pure mass, and we take it mu square negative, which you need justification, and maybe in other theories we will understand it better. So this is a physical parameter that we have so far, lambda and v, out of this potential. Is this answer your question?
Yes, yes.
Good.
Okay, my another question is about this hierarchy in the masses of particles.
Yes.
Is there any theory beyond the standard model that could explain this in a proper way?
Yeah, supersymmetry could explain it in a very nice way. Extra dimension, they are trying to explain hierarchy problems, but not in very. I like all direction of standard model beyond standard model because we don't know which one is real life will choose. But anyway, but supersymmetry, I would tell you when we go to supersymmetry that it's in very nice and very elegant way to solve the mass hierarchy. In fact, because simply the loop diagrams that you have seen now before the Higgs mass radiative correction of the Higgs mass, you will have, instead of F bar F running in the loop, you will have something called super partner. So this is fermion, you will have some scalar field running in the loop with the same mass, different sign. So the loop will be canceled completely, and the correction will identically zero. Of course, the supersymmetry is not exact, it should be broken. So we break it in the way to generate logarithmic divergence, not quadratic divergence, and the divergence will be similar to the electron mass. Not that. So, to my knowledge, really the best scenario for solving hierarchy problems of the Higgs mass is a supersymmetry.
Okay, Professor. The last one, sorry, is which energy scale are we expecting to obtain some kind of signal? Energy scale. Energy scale, yes. At which energy scale we are hoping to obtain some signals of supersymmetry in the experiments?
Keep this to the lecture of the supersymmetry. So far today, I'm trying to convince you with how elegant and how really nice, and it was not simple. It takes many years. If we started from 30 to till now, we are constructing and improving our construction of the standard model. So we have a very nice theory, but it cannot be ultimate theory, cannot be the final theory, and we have evidence that takes us to something beyond the standard model. So the challenge now is really to find out which type of scenario beyond standard model and how to improve it and how to propose the signals, as you said, because we cannot, supersymmetry is elegant and theoretically motivated, and as we told you, it's an extension of a space-time symmetry, blah, blah, blah. All this is nice mathematically. Physics needs observation, need verification, experimental. So unless we discover some specific prediction, new particle, new predictions, we will not be able to say this is a true thing. So yeah, keep it for next lecture. And in each one of the models we will consider in the next days, we will come back to the problems and how we solve it, or we complicate it more and more. Sometimes you try to solve the problem and you find that you make it much more work. And this is really the case in some scenario like SU5, for example. We will see.
Okay, Professor. Thank you very much.
Okay, so if there is any other question or comments from people online, don't feel shy. Please ask. Whatever you have in your mind, just ask. Okay, so all of you studied standard model before? Not very seriously, but studied. Yes. So we don't need to assign standard model to anyone. The assignment will come when we go to beyond standard model, because this is a new part, and we will see who is interested. I think is your name is Albert, or your name is what?
Gustavo.
Gustavo. Okay. Gustavo is from where?
From Peru. I did the master at EAIFR.
Ah. No.
If you forget about the fact that the is like a matter and you just want to give mass to bring up by matching like the difference with the mass. So then what's the is there an issue with that apart from the naturalness of the mass?
If you assume dark matter will be solved by modifying graphs.
Yeah, let's forget about that.
Dark energy will be modified by some modified graphs. Forget about inflation and cosmology. Baryon asymmetry. Forget about it as well. Baryon asymmetry. CP violation. You need stronger phase transition, and you need stronger CP. It's not in standard model. Well, if you forget about the dark matter, dark energy.
This is a cosmology.
No, but it's not cosmology, because you go. This is particle physics, cosmology interplay. So, but CP violation is not cosmology, really. But anyway, if I agree with you, if you add right-handed neutrinos, high scale, and you manage with type 1C, so you generate neutrino masses, and the second right-handed neutrino is very heavy and decoupled, and we remain with a mass standard model plus massive neutrino.
But can you just do it without just adding mass at the
you don't want even to write. You don't really want even to add right-handed neutrino.
Yeah.
Just mass term. But this mass term now you will have fine tuning of order 10 to minus 11.
So that's
you need to explain. That's an issue, but naturalness. But if you are happy to live with some, because you already ignored several things, yeah, then you remain. Maybe this is alive, unless LHC, because there is some fluctuation from time to time, some observation which is not consistent with the standard model, related to flavor, related to heavy scalars, and so on, neutral Z prime. Unless we got something like those, okay, we will continue the standard model, and all this list of questions I mentioned, it will remain unanswered. Which is something I don't think our physics usually continue like this. I think we usually try to answer any small question and then open for us new world. So I hope it will not work in the way you are proposing.
I was just asking you
if
there is any internal inconsistency.
No. It's essential standard model is consistent so far, unless the LHC with high energy round 3 or high luminosity gives some specific, kind of conflict with the standard model prediction. So far, there is nothing. Dark matter, as you said, I could solve it by some other way. Especially all the detection of the dark matter underground in the sky is still negative results, not the same for other things, small things that we can leave without really care about it. Okay, then we will continue with a standard model. Who cares about unification of the forces? Who cares about answering fundamental or physical or philosophical questions? We'll continue. But I hope, and I don't think it will continue like that.
Fair enough.
But in principle, there is nothing to prevent this scenario. In fact, if we failed with LHC at much higher energy, maybe this is our own solution. Yeah. Very pessimistic solution. Okay, so I was saying, yes, next lectures we will discuss different scenarios for the standard model, and maybe if Gustavo is interested in supersanity, he's welcome to explore it more and more beyond because it will be very difficult for supersanity to give it in just one lecture, so I just highlight a few things in that. And as I said, it's up to you. We want a detailed model, fine. We want to highlight different models, and each one will do his exercise by himself. This will be perfect fine as well. Okay. It seems no more questions or comments. I want positive comments, not pessimistic comments. Can we have some hope that we will discover something soon? Okay, you know, there is some really fluctuation, at least 2-3 sigma, but unless we get some real prediction, it could be as you said.
Right.
No, but your model could work even better if you assume right-handed neutrino and you make it heavy decoupled with scissor. And in your end, just a standard model with neutrino masses, even explained. But the right-handed neutrino heavy is decoupled. You don't go. My runner react, yeah, this is will be double beta decay, which could also depend on the, you know, the mixture between left and right. But if you decouple right, still, you know, you can be even safe. But at least you need to overcome the issue of the small masses and the explanation of the small masses. You will have very large masses, but who cares? We are open, you know, we never know how it goes. Okay, so if there is no more questions or comments, maybe we stop here and we'll see you tomorrow at 10 o'clock as well. Okay, thank you for coming and for joining online. Bye.
Thank you very much, Professor.
Bye-bye.